Hello, this video is for Stat 360, handout number 11, Part A, and includes pages 1 through 11. Okay, let's go ahead and get started. The data set that we're going to use in this handout is the Impact Crater data set, and this is included in our Google folder for handout 11. So handout 11 covers the idea of an indicator variable in a regression model. These are sometimes called dummy variables as well. We're going to be working with the Impact Crater data set. The response variable for the model that I'm going to be fitting is going to be the diameter here. And the predictor variables that I'm going to be considering are height and also sand type. Now what's different about handout number 11 is that one of my predictor variables is going to be a categorical variable. It's either coarse or fine, as we have here. We're going to initially fit this first model. We'll call this model number 1. It has the following form here and a constant variance function. Inside of JUMP, we can go ahead and create a scatter plot. But this does not indicate the two different types of sand. If you want to indicate the two different types of sand, one way that we can do that is to color or mark by a column. So inside of JUMP, I can select rows and then color or mark by column. I can specify that I want to mark by sand type. And when I do that, I will have two different marks or colors for any graphic that I compute or create in JUMP. In those graphics, or for those graphics, the blue will identify fine and the red will identify coarse. That color scheme will work beyond just this single graph that I make. So JUMP uses something called dynamic linking, which again will allow me to differentiate between the sand types, not just on this plot, but on any plot that I create. So let's go ahead and fit this initial model, or model number 1, in JUMP. I'm going to select Analyze Fit Model, and then I'm just going to put diameter in the response box here, and height and sand type down here in the Construct Model Effects box. So let's go over to JUMP and show you how to do that. Select Analyze, Fit Model. Diameter is going to be my response. And I have two predictor variables, height and sand type. And then just click Run up here when I'm... Now that's going to fit a regression model for height. That will include height and also sand type. Now you can see on this scatter plot that we get that the points have not been identified by color. That's because I have not went and specified that in JUMP, so I need to do that. So again, to do that, I'm going to go rows, color or mark by column, and then I want to use sand type to mark by. And again, the red is going to be for coarse sand. The fine is going to be for blue sand. If you select this Make Window with Legend, then JUMP will create its own window that will always contain this legend for you. So now we can see that those points, if we go back to our scatter plot, those points have now been color-coded red and blue with the corresponding sand types. Down here, towards the bottom, I'm going to have all of my regression output. So that's what we're going to talk through next. So the regression output from model number 1 is provided here. We can see that the R-squared is about 32%, so I don't have a great model here. My root mean square error value is 1.43. So my scale here is about from 3 up to about 10 or so. So my root mean square error is just the average residual. Now those residual values, the blue dots are using the blue line as its mean function, and the red dots are using the red line as its mean function. So those residuals are being computed from its respective mean squared and then added all up. That's what that sums of square error term would be giving us here. Here are the forms for the models. So for the fine sand, so if I have fine type equal, or sand type equal fine here, the appropriate form is simply going to be the intercept plus the height term. So it's going to be 4.91 plus 0.02 times height. Now that's for the fine sand. So that's going to be the blue line here. That would be the equation of the blue line. The equation of the red line is going to just deviate slightly from that because I have another term here that is indicating the coarse sand type. And it looks like I need to reduce the y-intercept by negative 0.4 here. So the model for the coarse sand has the following form. 4.91 plus 0.02 times the height. So I definitely use those first two terms. But now I have this extra term here, okay, due to the coarse sand type. And I'm just going to subtract 0.4 there. So my new y-intercept is going to be 4.91 minus 0.4, or 4.51. So the slope, or excuse me, the equation for the red line is going to be 4.51 plus 0.02 times height. Now we might notice here that the height is the same for both of these. And that's a side effect of the model that I fit. So when I fit this model up here, what is actually happening is I'm getting or allowing for two different y-intercepts, but I'm not allowing for two different slopes. So in some sense, I am restricting the model. I am forcing the model to have parallel lines here. So let's go ahead and interpret then what each of those quantities mean. The beta 0 hat, the 4.91, is going to be the value of the y-intercept when the sand type is equal to fine. So if we take this blue line and extend it all the way down to 0, we're going to end up, it's going to end up crossing that line at 4.91. The 0.02, which is the beta 1 hat in this model, is going to be the slope for both sand types. So the 0.02 is here, and it's also here for coarse sand. So 0.02 is going to be the slope for those. Now this model has parallel lines because the model that I fit forces the slopes to be the same. The beta 2 hat just represents the change in the y-intercept between the fine and the coarse sand. So the negative 0.4 just represents this difference between these two lines. It's actually the difference down here at the y-intercept, but these lines are parallel, so it would be the difference between the two lines at any point. So we can see that when the coarse sand is used, the diameter of these craters is reduced by that amount, by 0.4. So how does this model fitting actually work when I have a categorical variable in the model? So what JUMP does, or what our software does, is it actually creates these indicator variables, or dummy variables. So if you think about the design matrix, or the X matrix, I have a column of ones, I have the height here, and then I have the values for the different sand types for every observation. I need to take the inverse of this matrix. That's how we obtain our estimated coefficients from the model. If we go back to, I think it was Handout 8 or so, we talked about how to get those estimates in R. You have to do some matrix algebra to get those. But you're not going to be able to do matrix algebra with coarse and fine in the matrix. So what our software does is it just converts the coarse and fine values to ones and zeros. In that sense, it's an indicator, just indicating the sign type, the sand type. So when a categorical variable is included in a regression model, a new term is created. This new term is called an indicator or dummy variable. And all that variable does is simply indicates what type of sand I have. If I have a variable with just 2 levels, which sand type does, then I need just a single indicator variable. In part B of this handout, we will consider what has to happen if I have more than 2 levels. So what is the model form for sand type equal coarse? Well, I'm going to have beta 0 plus beta 1 times height plus beta 2 times the sand type. But in my indicator variable, when I'm dealing with coarse sand, the sand type variable is just a 1. Doing a little bit of algebra and putting terms together, we can see that my y-intercept is going to be beta 0 here plus beta 2. So the y-intercept for the coarse sand is going to be beta 0 plus beta 2. The slope is just going to be simply beta 1. What's the model form for fine sand, Now I'm going to put sand type equals 0 in this model, and that means that this term right here is just going to go away. The beta 2 is not going to appear in this model, and I'm going to have simply beta 0 plus beta 1 times height. So terms will disappear for the fine sand. In our regression output, that is why JMP is not showing me sand type equal fine, because that term actually has a 0 coefficient. So it's only showing me the estimated parameters for coarse sand here, because these would be 0 for fine sand. Okay, so what do these tests mean? Well, let's look at test number 1. Test number 1 is just going to be testing whether or not beta 0 is equal to 0. And that's going to be testing the y-intercept for the level that has been set to 0. So here that's going to be fine sand. Beta 1, the second test, that's just the slope. And that's testing whether or not the slope is different from 0 for both levels, for coarse sand and for fine sand. So it's combining those two groups. Beta 2 here, which is just going to be the shift in the line. So that's just testing the difference between the y-intercepts between the two levels. Now again, for a parallel line model, we could be testing that difference at the y-intercept, or we could be testing that difference anywhere along that line, along those lines. Okay, how about page 7? What we're going to do now is allow for a less restrictive model. We're going to allow for the slopes to be different. We still have a constant variance. So what that model has is one additional term here. And this is an interaction term. An interaction term just means that it's a combination of other terms. So we're using new terminology here with the idea of a term. I called sand type an indicator term. What a term means is it's not necessarily, so that if I say the sand type variable, what I'm talking about there is the quantities or the levels coarse and fine. But if I talk about the sand type term, what I'm talking about is the indicator, the 1 and 0. Here's another new term. This term here is a combination of variables. It's actually a combination of a term and a variable. So we have predictor variables, but we also can start to add different types or functions of predictor variables, and we call those terms. Okay, so the sand type again is just an indicator variable or an indicator term with a 1 and 0 setting. The height times sand type here, So this variable right here is called an interaction term. It's an indicator variable as well, multiplied by the height. So it's going to have values height or 0 here. So if we go back to our design matrix, it's not going to have values 1 and 0, but it's going to have values 25 and 50, and then for fine sand, they're all going to be set to 0. How to fit model number 2 in JUMP. We're going to put diameter here in the response box. Model effects, I'm going to have height and sand type, and then I need that interaction term. To create the interaction term, what I need to do is highlight 2 of these variables at once, holding the control button down, and then clicking cross, and that'll put the interaction term in the model. The other thing that we can do underneath the red drop-down menu here is to deselect or uncheck center polynomials. So let's go over into JUMP and show you how to do that. So this is the output from model 1. I want to fit another model, which I will show you a shortcut. From the red drop-down menu, you can say redo and then relaunch analysis. When we start fitting lots of models, this is kind of nice because what that does is it brings up the fit model box that we use to create this output. So again, where did I get that? From the red drop-down menu, redo, relaunch analysis. Now this output here is from model number 1. I want to create a new one that has the interaction term in it. So all I need to do that is to select height and sand type, holding the control button down to select both, and then just say cross. From here, I want to select or deselect center polynomials. I want to uncheck center polynomials. And go ahead and hit run. This output here is going to have one additional term in it. So looking at the output here, zooming in a little bit, we can see that our parameter estimates has one additional term. My R squared didn't move much. My root mean square didn't move much. So this additional term is not really helping me much, but I have included one additional term in the model. Next, what I want to show you is just what is the difference or what is the effect of the center polynomials. So on the left side here on page 8, I have unchecked center polynomial. On the right side, I left center polynomials checked. The only thing that indicates whether or not you've centered the polynomials is how JUMP has expressed the predictor variable for height. So here you can see that it has height minus 112.5. 112.5 is the average height. And it is taking the heights and subtracting or centering that variable. The only difference that I have in these parameter estimates and the probabilities or p-values is for sand type coarse. Here the p-value is 0.1679, and over here the p-value is 0.0018. So what is the effect of center polynomials really having on my model? For that variable, so for this variable right here, the 0.365 is the change at the y-intercept. Okay? So that test is for whether or not there's a change between the two lines at the y-intercept. So visually, that's going to be actually doing the test over here at 0, at the y-intercept. The p-value here is not significant. So that means I really don't have a statistically significant difference here at the y-intercept. In other words, these two lines are too close together down here at the y-intercept. I'm going to get a different p-value if I do the test at the y-intercept compared against if I were to do the test somewhere else, because these two regression lines are no longer parallel to one another. So if I decide to do the test not at the y-intercept, but up here in the middle, or average height, it turns out that I do have a significant difference there. So I can get different results depending on where I'm testing. If I'm testing for a difference down here at 0, I don't have statistically significant difference. But if I test here kind of in the middle of my data, then I do have. And again, the reason I have differences between these two is because these two lines are not parallel to one another. So as far as my estimated regression models and what the models look like, when sand type is fine, I'm going to pick up the 4.91 here and the 0.0157 here. So that's going to be the equation of the line for fine. This is the equation of the line for fine. And fine here on my graph, I think, was the blue line. The equation of the red line is going to have a different y-intercept and different slope. So if we put those pieces together, 4.91 is where I start with, but now I need to decrease the y-intercept a little bit. And again, it's a decrease of the y-intercept because I have, or am using here, the output from centered polynomials being deselected or unchecked. So that would be the correct difference at the y-intercept. For the slopes, I have 0.0157, and then I need to decrease it just a little bit. There's not much change in the slope between the two models here. 0.0157 versus 0.0156. So even though these two models look like they're parallel to one another, they technically have different slopes. Here's the p-values. I have 4 of them listed here. P-value number 1 is just going to look at the y-intercepts for sand type fine. P-value number 2 is going to be the slope is non-zero. So that's indicating that it's non-zero. Now that's again for both levels. Beta 2 is going to be the third test here. And that is saying that I do not have a difference at the y-intercepts. Again, this is the centered polynomials deselected here. So this test right here, test 3, is for the y-intercepts. If I had selected centered polynomials, test 3 is going to again be at the average. The last one down here is, for that last term, is testing the beta 3 in my model, and that's just trying to determine whether or not I have differences in slopes. Okay, some final comments. To be honest, test number 1 and test number 3 are not all that meaningful. Test number 1 and test number 3 are testing what's happening at the y-intercept. And if we go back and look at our graphic, the y-intercept is going to indicate, well, what happens when I don't drop anything? When it doesn't drop for any height, what can I expect the diameter to be? I mean, that doesn't even make sense here. So in practice, test number 1 and 3 oftentimes do not make sense or are not relevant. Comment number 2 is regarding that center polynomial again. So test number 3's p-value is significant if centered polynomials is checked. We do have a difference between the sand types when the projectile is dropped from an average height. Again, that height is at 112.5 for this data. Now, the big reason that I have differences between this test from centered and non-centered polynomials is because of the standard error differences. Recall that I'm going to have much more variation in my estimated regression line over on the edges than I do in the middle. Okay, so if we go back up here and look, if I do this test on the edges, these regression lines are going to have a lot more variability over here on the edge than they do in the middle. That's the whole idea of the leverage. So the test in the middle is certainly going to have a smaller standard error. And if we go back up and look at that column, the standard error column, for centered polynomials, you can see that that standard error is cut in half. And the reason that standard error is so much smaller, again, is because I'm doing that test in a spot where the regression lines are not moving very much. Over here, that standard error has to be substantially larger, which makes my test statistic not as big. It also, if I were to do test number 3 on the centered polynomials, this is a more intuitive test. Do I have differences here kind of at a typical height? And that's what this test is answering. And that would be yes, I do have differences here. Now if I slide down to height 50, I'm going to have to create a custom test for that, because again, these two lines are not parallel to one another, so the p-value is going to change if I slide down a little bit and want to do this test at a different height. You'll have to use the custom test in order to do that. How about comment number 3? Test number 4 seems to suggest that a model does not need to include two separate slopes. So test 4 here is there's no difference in slopes. And you can see from the graphic that the lines are nearly parallel to one another. So I probably don't need two different slopes. So let us consider the following custom test. So I have model number 1 here, or model A maybe I can call it, which does not involve sand type. That's a typo there, so it actually does not involve sand type at all. So can I model the diameter just using the height and ignore sand type? Or model B would be, does sand type provide some useful information to me? So this is I'm going to use the big F test to do this. We can see that model A, or the model under the H naught here, does not have sand type in it, and it is a subset of model B here. And in particular, I'm interested in whether or not beta 2 is equal to 0 and beta 3 is equal to 0. So I could write that test equivalently by just asking, is beta 2 equals 0 and beta 3 equals 0? What that means practically is, or what this test is practically trying to do, is determine whether or not I need sand type at all. Model A would be no sand type in the model, and model B does involve sand type, allowing for different slopes and different y-intercepts. So how to do that test again? Let's go back over here to our output. From my drop-down menu, I'm going to select Estimates and Custom Test. And down here at the bottom, I'm going to, let's put that in the middle of the video for you. This is going to be a test for sand type. I'm testing two parameters, so I need to add a column here. Beta 2 is going to be picked up here, so I'm going to put a 1 there. And beta 3 is going to be the interaction term here, so I want to put a 1 there. Now I want to know whether or not beta 2 is equal to 0, so I'm going to leave this as 0. And I want to know whether or not beta 3 is equal to 0, so I'm going to leave this one here as 0. Go ahead and say done. And this is the output that I've included in the notes here. The prob bigger than F is the p-value that I want to use here. So down here, the probability here is the p-value for that test. The p-value here is 0.0076. So what's my conclusion here? A model that includes sand type is better than a model that does not. So practically what that means is sand type is giving me some information about what's going on. So what is the correct model? Well, the correct model, at least what I would do next, is it doesn't look like I need this two separate slopes model. This p-value is very, very large here. So I think in this situation, the best model, at least up to this point, is model number 1, where I have two different y-intercepts, but I don't need two different slopes. And if we go back up and look at that output from model number 1, we learned that there is a difference between the two types of sand here. Test number 3 is indicating that I do have a difference between the two types of sand. But the effect of height is pretty consistent. I don't need an interaction term. I don't need two different slopes for this data. All right, the last thing I want to do is just show you a picture of the residuals, because the residuals are showing that I have something else going on. So the left display here is just the residuals from that model, from actually model number 2. So here's the residual plot. And you can see that I have 3 different groupings here. I got kind of a group of points here and here and here. Now that's not good in a residual plot. In a residual plot, we just want random scatter. What this is indicating is that I'm missing a variable, or I'm missing information. And it's pretty straightforward in this example. The 3 different groups are because of the 3 different projectile types. Remember, in this experiment or this study, they were looking at glass ball, steel ball, and wood balls. And if I color or mark by projectile type, and not by sand type, I can clearly see these 3 groupings that are appearing in my residual plot. So we're going to want to include projectile type in a model. And that's what I'm going to do on part B of this handout. All right, that does it for Handout 11, Part A, pages 1 through 11. Thank you.